Hi, my name is Jeff, and today we'll be talking about the expectation maximization algorithm, which is an iterative method to find the maximum likelihood of parameters in models where the model depends on unobserved latent variables. And latent variables are essentially just variables that are unknown to us. However, their variables are pretty much inferred from other variables. Um, this EM algorithm is an iterative process between two steps: the expectation step and the maximization step, or in this case, we'll just say E step and M step respectively. Now, the E step is as follows: for I equal to 1 dot 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 to M, fill in the missing data x of I according to what is most likely given the current model at mean, and the M step is just to run the ML for complete data, which calculates the new model of the standard deviation as well as its variance, or as you could say, standard deviation. So here's a little image describing what the difference between k-means clustering and EM clustering. So here's original data. You can see that some of these points are not even associated to it. And so k-means is just setting these three centroids, at these positions, right? And they have a set radius. And so anywhere the points in the radius is just associated with it, as well as this one. And it doesn't seem right, because you think that points in this sort of circle shape would be associated with one cluster. So this is what EM does. It includes standard deviation inside of its algorithm rather than just having just a mean. And this is what it creates, this unique shape where it doesn't associate points that it thinks is probably the other ones. There's confidence levels to these points, and so we can have an example of where we use two Gaussians for this expectation maximization algorithm example. And so what are Gaussians? Gaussians are basically just a bell curves, and here's an image of a bell curve. You can see here, right dab in the middle, this is the mean of the Gaussian. And so you can have like the mean can be any value, really, and it can be shifted over, shifted to the left, right, whatever, and it can be changed, as well as the standard deviation, which is the difference between these 2 points, these two little low lines, which is like 0.5. So that's the variance, or the standard deviation. And so this bell curve is just sort of what the Gaussian is, and that's what the standard deviation just changes the shape of it. So that's that. So basically, A will run the probability density function for each of these x of I points, which are just the points on the graph, in Gaussian A. So this is then it calculates the Bayesian and posterior of the combination of both A and B, which are the priors, which are assumed to be equal for now. And here it is. This is that. So so A of I is very it's the confidence level that x of I is to Gaussian A. So A of I. So the x, let's say for x of 1, it can be A of 1 for that. And this variable is tied with that, and basically that's that. So what this A of I value is, that represents how confident x of I is to Gaussian A, or the posterior of x of I. And if let's say you want to do what about the confidence that x of I is to Gaussian B? Well, that's just 1 minus A of I, since A of I can't be greater than 1, or less than 1. So, or less than 0, I meant. So yeah, it's between 0 and 1. What makes this a little bit really special is that it labels the data points, right? And we'll elaborate that more a little bit later. And an important idea to note is that these points are not 100% this or that, or that and this. Rather, these points can be in between these two Gaussians. So let's say the point is in the middle between these two Gaussians broken on these two sides, and it's sort of like in between. It doesn't know whether it's this one, this Gaussian, or that Gaussian. So basically, it's in between. So the A of I of this point could be like 0.5, and the B of I value of this point could be like 0.5 as well. And so it's in between. And so What I'll elaborate why these two values come into play with the expectation maximization element. And so this entire process of just finding the confidence level, the PDF of each variable to each Gaussian is, and the A of I, B of I. This is all part of the E step, the expectation step. And so the next step is the maximization step, which essentially just adjusts the size of the Gaussians according to the points that are likely to be its own, which means that at its mean value as well as its standard deviation value. And so you can see here that the mean of A, we're looking at cluster A for this example. The mean of A would equal to A of 1 times X of 1, A of plus A of 2 X times X of 2, yada yada, until A of n times X of n, all over the A values. Now you might be wondering, well, why are we including all the X values when we know that some of these X values are probably not associated with cluster A? And this is because this is where the A values come into play. And so let's give an example. Let's say that this X of 1 variable right here is most likely to be associated with this cluster A. So this A of 1 value associated with this X of 1 value is probably very high, probably close to 1. And so essentially this is basically just 1 times the value over 1. As you know, mean is just all the values added together over the number of values there are. And so that seems pretty pointless, because you're just it's just finding the mean over, you're just multiplying 1 to the variable. However, we'll get over to this one, X of 2. Let's say X of 2 is not even, it's probably not associated with cluster A, but you just have a little there might be a chance. So A of 2 probably could be like very low, close to 0, probably like 0.1, 0.05-ish. And so that's essentially just saying that 0 times X of 2. And so here A of 2 would be close to 0, making like literally no contribution, very to little no contribution to this overall mean. And so you might be saying like, well, that doesn't answer my question. It's still a little bit pointless. But that all changes when I mention the points that are in between, that are not 100% this or that. It's probably in between. Let's say X of n is in between. So this A of n could be 0.5, and this A of n right below here contributes a little bit to the number of values there are. Well, now you can't really say it's the number of values there are since it's like 0.5, but it contributes a little bit as you with reasoning. It changes a little bit. So basically, that just the beauty of the EM algorithm is that it includes all points, and every single point just changes the Gaussians just a little bit. And so, well, what about the mean of B? Well, what about the mean of the second Gaussian that we mentioned, cluster B? Well, you just say the mean of B equals to B of 1 times X of 1 plus B of 2 times X of 2, yeah, and so on and so forth until like n, variable n, and you just say B of 1 plus B of 2 plus ... ellipses, or plus B of n. So that's how you get the mean of the B. As you know, B of I is just 1 minus B, A of I. You also need to change the standard deviation of each Gaussian, and so B of 2, the variance of B of a cluster A, I meant, is just, it uses the same sort of same method. So A of 1 times the difference between the mean and the value, and squared, and so all over that, which is pretty self-explanatory. That calculates the standard deviation. You can also say the standard deviation of B is just all of that, but every single A value is just replaced with B according to the X that you're referencing. And then you also have here's a little, this is the M step, the maximization step, which is just adjusting the Gaussians, as I said before. And this is repeated multiple times until the mean, like it doesn't move at all until a certain threshold, obviously. Let's say it's just moving between like negative 0.1 and 0.1. Well, if it just keeps like shifting over and over and over, you can just say, well, if it's in that little window of values, it can just stop, and that's convergence or whatnot. And so here's a little visual process of showing how E of M algorithm works. You can see that these two clusters for a split second were these two random locations with very large, very wide standard deviation values. And so after one iteration, it is quickly adjusted to this area and this area as well. And the red Gaussian realizes that these points in the middle right here are probably not its own. It's probably the yellow Gaussian. Therefore, it sort of shifts over and centralizes towards this area, while this sort of expands its standard deviation to accommodate for these ones. Yeah, so you can see that the applications for these is that this EM algorithm is basically the base of many unsupervised learning clustering algorithms in machine learning. And like you can see Gaussian mixture models. You can also see it's a very base. It's the very base of these unsupervised clustering algorithms. And examples of such are used in our societies at advertising platform segmenting the population to smaller groups with similar demographics and purchasing habits to make their ads reach specific people / audience. So yeah, it's just more effective ads. And B, grouping house listings into neighborhoods for easier navigation of listings. So these are just some of these examples of E of M, the EM algorithm just showing off its talent in our real world. And I can just give you a quick demo of what it is. So this is a 2D example of what EM can do. And so let's say you have Gaussian red R, which is blue, red, and then you have Gaussian B, which is blue. And as you can see, this is probably the mean is probably around here. The mean for this Gaussian is probably around here. And the first quote unquote step is that it just associates points to itself. So yeah, the E step associates, okay, this point right here, that's very close to this mean, rather than this mean right here, the blue Gaussian's mean. So therefore, it just associates this point with red, and well, now it considers all the points to our right, and it says, oh, this is probably blue, because it's closer to this mean than it is to this mean. So after it associated all these points to the specific Gaussian, it redraws the Gaussian. So in this case, the Gaussian for the red Gaussian hasn't really moved. It's just shifted up probably a little bit. The Gaussian B for blue, however, has changed significantly, as its mean has probably changed much more than its previous predecessor, whatnot. And so now it recalculates the standard deviation according to all these points. It's just that probably the B of 1 of x of 1, this is x of 1, is probably very close to 0. Therefore, it's probably not even considered part of this algorithm. It just excludes that, but it still considers it in its algorithm as shown in one of the here, and as well as the standard deviation as well. So now it doesn't just stop there, because it expects these two mean values to change over the course of several iterations. So that's just after the first iteration. It goes to the second iteration, which means this Gaussian probably shifts over a little bit, since these points are probably associated with it, and the blue Gaussian probably moves a little bit further out, and it just associates these points with it. And after a while, these two Gaussians sort of move around just maybe a little bit. Maybe it moves here, maybe it moves there, whatever it needs to do to get a better sense of itself. And after a while, it reaches convergence, where basically this mean barely moves. The standard deviation doesn't really change at all, and that's when it stops. And that's when you have two Gaussians that you prior to starting the EM algorithm have stated. So there are two, and yeah, after it reaches convergence, it stops, and there you go. You have two Gaussians. So yep, that's the expectation maximization algorithm if you